How can we solve poker or other games with sequential actions and incomplete information? Well, that's a hard problem in general, but in this video we'll explore the counterfactual regret minimization algorithm, which can solve small to medium poker variants and other two-player zero-sum games, and which also serves as the basis for other algorithms that have had success on much larger and more complicated games. Here I've drawn the full game tree for the simplest possible variant of poker known as Kuhn poker. This game has 2 players and a total of 3 cards, king, queen, and jack. And at the start of the game, each player pays an ante and then gets dealt 1 card. Then there's a single opportunity to bet with a fixed bet size of 1. And after a bet, the opponent gets a chance to call or fold. And then, if either player folded, the one who didn't wins the pot. Whereas if neither player folded, then the player with the higher card will win. And so, in the extensive form game tree representation, Kuhn poker starts with a move by nature corresponding to the dealing of the cards. And there are 6 possibilities for how the cards will be dealt to the 2 players that all occur with equal probability. Then the first decision in the game is when player 1 decides to bet or pass. And at that point, there are 3 possible information sets corresponding to player 1 having been dealt a king, or a queen, or a jack. And each of those information sets contains 2 nodes. In the information set where player 1 was dealt a king, there's a node corresponding to each of the states for what player 2 could have been dealt. So we have a node for player 1 was dealt a king and player 2 a queen, and another node for player 1 was dealt a king and player 2 a jack. Then, after player 1's action, on player 2's turn, there are 6 different information sets. Because player 2 could have been dealt 3 different cards, and they could have seen 2 different actions by player 1. So for example, this orange information set contains both of the nodes where player 2 was dealt a jack and then saw player 1 play the action pass. And that information set contains 2 nodes because player 2 doesn't see the part of the state corresponding to what card player 1 was dealt. When they received a jack, it could be the case that player 1 got a queen or that player 1 got a king. Finally, if player 2 plays the bet action, then player 1 gets a chance to call or fold. And again, we have information sets for player 1 where they don't know what card player 2 is holding. And so in total, player 1 has 6 information sets. They have 3 information sets at their first turn and 3 more at their second turn. And we can label each of those information sets according to what history player 1 has observed up through that point. In the first 3 information sets, all that player 1 has observed is the card they've been dealt, and so we can label those information sets king, queen, or jack. But if the game arrives at one of the bottom 3 information sets, then player 1 has observed a history that includes the card they were dealt, and then they would have played the pass action, and then player 2 would have played the bet action to get us here. And so we can label each of these 3 information sets with the histories king, pass bet, queen, pass bet, or jack, pass bet. Likewise, we can associate each of player 2's information sets with the history that gets us there. For example, we arrive at the orange information set by player 2 having been dealt a jack, and then player 1 choosing the action pass. And so that information set corresponds to the history queen pass. So because each player has 6 information sets, and at each information set there are 2 available actions, we can represent a behavioral strategy for either of the players as a 6x2 table with a row for each information set, and then in the column for an action, we put the probability that the player will play that action when they're in that information set. In both of these tables, I've labeled the first column with a $sign to indicate the call or bet actions, because those both involve adding a dollar to the pot. And I've labeled the second column for the fold or pass actions with a null symbol indicating that the player isn't adding to the pot. And so, in the current strategy that I've written out for player 1, if they are dealt a king, then they will play bet with probability 2/3 and pass with probability 1/3. Whereas if they're dealt a queen, they'll bet half the time and pass half the time, or with a jack, they'll bet 1/3 of the time and pass 2/3 of the time. Then, if we reach one of the histories where player 1 passed and then player 2 bet, then player 1's strategy says to always call if they have a king, to always fold if they have a jack, and to mix 50-50 if their card is a queen. I've given a similar strategy for player 2, where they are more likely to call or bet when they have a higher card. And just like we did last time, we could use this profile of strategies to compute beliefs and expected utilities and check whether the profile is an equilibrium. And as we know, the procedure to do that is to first walk down the game tree computing beliefs at every information set, and then once we have the beliefs, we can walk back up the game tree computing expected utilities. And that same procedure of calculating expected utilities for each action at each information set, which we used last time to check whether a profile was an equilibrium, will now be a key step in our counterfactual regret algorithm for identifying an equilibrium. The core idea of counterfactual regret minimization is that we're going to perform a regret matching update at every information set in the game. So just like with normal form regret matching, where we keep track of a cumulative gain for each action, and then normalize the gains into strategies to get a profile, we will be keeping track of a cumulative gain for each action, but we'll have to do that separately at every information set. So for example, at the QPB information set for player 1, since player 1 has 2 actions there, they will have a gain value for each action, and this will track the gain that we've seen so far across all of the iterations of our algorithm. And if so far our cumulative gain for the call action is 3 and for the fold action is 3, then when we normalize, we will get a probability distribution of a half, which tells us how player 1 is mixing at this particular information set in their current behavioral strategy on this iteration of the counterfactual regret algorithm. And then we will use the current profile to compute new gains at every action at every information set. And so when we do that calculation, if it turns out that against the current profile at this information set, the gain for call is 0 and for fold is 0.5, then we will add those gains onto our cumulative totals and use those in updating the profile for the next iteration. But in extensive form games, there is one further wrinkle, which is that before we add on the gains to our cumulative total, we have to weight them by the probability that the information set would be reached if the player tried to do so. We'll come back to how those probability weights work and why in a little bit, but first we should walk through the procedure for calculating the gain. As usual, an action's gain is how much better it would perform than the current strategy. So we need to calculate the expected utility for each action and the current mixture by traversing the game tree. Which means we need to start at the top and work our way down, calculating the belief distribution at each information set. Beginning with player 1's first move, where they are uncertain about which card the opponent is holding. The only randomness that has happened so far is the move by nature, and that puts equal probability on each of the possible deals. So, with a 1/6 chance of ending up here and a 1/6 chance of ending up here, the conditional probability of being in this node, given that we're at this information set, is a half. And in this table where we are recording the beliefs at each information set, I've labeled the columns H for the opponent has the higher of the two possible cards, or L for the opponent has the lower of the two possible cards. But which cards are possible will be different based on what the player knows. So here, H means that the opponent has a queen, and L means that they have a jack. Whereas, if player 1 has a queen, then this column means player 2 has a king, and this column means they have a jack. But just like at this information set, there's an equal probability of each of the states in player 1's other two initial information sets. And then we need to continue walking down the game tree and updating the beliefs. Now that we've arrived at player 2's turn, we need to figure out for each of player 2's 6 different information sets, what's the probability of being at each of the 2 states in that information set. I've just noticed that the color of my bullet points does not correspond to the color of my information sets. And now that that's fixed, let's start by figuring out the probability of each of the 2 nodes in player 2's first information set. If player 2 arrives at this blue information set, where they were dealt a queen and then player 1 played bet, they know that there's a 50-50 chance that player 1 was dealt a king or a jack. But since player 1 is randomizing their action and using different probabilities based on which card they were dealt, the probability of seeing player 1 play bet might be different in the case where player 1 was dealt a king versus when player 1 was dealt a jack. And so to figure out the probability that we're in either of these 2 states, we need to calculate the conditional probability that player 1 has a king based on our observation that they played bet. So the probability that player 1 was dealt a king, given that player 2 was dealt a queen and saw player 1 choose bet, is, by Bayes' rule, equal to the probability that player 1 would play bet when they have a king, divided by the probability that player 1 would play bet overall in either of the 2 possible states. Given that we are at this blue information set, player 1 must have either been at the king information set or the jack information set, and those both occur with probability 1/3 according to nature's deal of the cards. And if player 1 was at this node, then at the corresponding information set, their strategy said to bet 2/3 of the time. So there would have been a 1/3 times 2/3 probability of getting to here. And we're dividing by the total probability of getting to either of these nodes. And the probability of getting to here, when we know player 2 has a queen, is a 1/3 chance that player 1 was dealt a jack, times player 1's probability of betting when they have a jack, which, according to their strategy, is 1/3. And so, when player 2 arrives at this blue information set, they calculate a 2/3 probability that they're at this node, meaning there remains a 1/3 probability of being at this node. And if we do the same calculation for the green information set, where player 2 was dealt a queen and then saw player 1 pass, there's still a 1/3 chance of player 1 having been dealt a king or dealt a jack, but now the probability that player 1 will pass with a king is 1/3, and the probability that they will pass with a jack is 2/3. And so upon arriving at the green information set, player 2 thinks there is a 1/3 chance that player 1 has a king, and a 2/3 chance they have a jack. But I really ought to be color coordinating these beliefs with the information sets. At the purple information set, player 2 has been dealt a jack and has seen player 1 play bet, and player 1 could have been dealt a king or a queen. So we need to look up player 1's probability of playing bet if they were dealt a king or a queen. Those deals each happen with probability 1/3. And then, if player 1 was dealt a king, they will bet with probability 2/3. Whereas if they were dealt a queen, they will bet with probability 1/2. And so if player 2 is holding a jack and sees player 1 bet, they conclude that there is a 4/7 probability that player 1 is holding a king. Then, at the orange information set, where they have been dealt a jack and seen player 1 pass, they see that player 1 passes with probability 1/3 when they have a king, and probability 1/2 when they have a queen. And so the conditional probability that player 1 has a king in this case is 2/5. Continuing now to the cyan information set, where player 2 has been dealt a king and seen player 1 play bet, player 1 has a 1/3 chance of having a queen or a jack, and if they have a queen, they bet half the time, whereas with a jack, they bet 1/3 of the time. So we get a conditional probability of 3/5 that player 1 is holding a queen. And finally, at the pink information set, player 2 is holding a king and saw player 1 pass. And in the event player 1 has a queen, they'll pass with probability 1/2, whereas with a jack, they'll pass with probability 2/3. And so the conditional probability that we are in the state where player 1 has the higher of the possible cards is 3/7. Now we finish our traversal down the game tree by calculating beliefs for each of player 1's final action sets, where for the first action set, we need to figure out the probability that player 2 was dealt a queen as opposed to a jack, given that player 1 has a king and the sequence of actions was pass and then bet. It occurs to me that in all of the calculations we just did, the number in black should not have been 1/3, because, for example, the conditional probability of player 1 having a king when player 2 has a queen is 1/2, not 1/3. But that didn't affect any of our calculations because the 1/3s canceled out every time and the 1/2s would have as well. And so in calculating our probabilities this time, we can just leave out the values in black from the initial deal because we know those probabilities were all equal. In addition, the probability of reaching either of these nodes technically depends on the probability that player 1 chooses to play pass at this information set. But since that will appear in all of the terms of our fraction, it too will cancel out. So technically, for calculating the probability of this node, given that we're at this information set, we would get terms that look like this, where we need to fill in probabilities from player 2's strategy of choosing the bet action in each of these information sets. In the green information set, player 2 bets with probability 2/3. And in the orange information set, they bet with probability 1/3. And so overall, the conditional probability of being in this state, given that we are in this information set, is 2/3. But since the black probabilities and the red probabilities all canceled out, and that will be true for each of these information sets, we can leave them out. So coming to player 1's next information set, where they were dealt a queen and passed, and then player 2 played bet, we need to look up from player 2's strategy the probability that they played bet in the pink information set and in the orange information set. In the case where player 2 has a king, they bet every time, whereas if they have a jack, they only bet 1/3 of the time. And so we fill in those probabilities to our Bayes calculation. And we get a conditional probability that player 2 is holding a king of 3/4. Finally, we come to the information set where player 1 was dealt a jack and then passed and player 2 bet, in which case the probability that player 2 has a king is the probability that player 2 bets with a king divided by the total probability that they will bet with either a king or a queen. And so we get 1 over 1 plus 2/3 for a conditional probability of 3/5. At this point, it's worth mentioning briefly that I've been taking a lot of shortcuts here, and that I will continue to take various shortcuts in the utility calculations we're about to do, but that if you were actually implementing this in code, you would want to make sure that you are doing a careful tracing node by node down the tree for the belief calculations and back up the tree for the utility calculations, and you would calculate the probability of arriving at each node and then use those in the belief calculation. And you'd also calculate the utilities at each node and then combine them to get the expected utilities of various actions. Now that we know the player's beliefs at every information set, we can use those beliefs in our traversal back up the tree to calculate the expected utility of each action and each information set. Starting from the bottom, at this information set, where player 1 is holding a jack, if they call, they will always lose 2, whereas if they fold, they will always lose 1. So player 1 gets an expected utility of -2 for the call action and -1 for the fold action. Similarly, when player 1 is holding a king, if they call, they will always get +2, and if they fold, they will always get -1. But at the information set where player 1 is holding a queen, if they fold, they'll still get -1, but if they call, they could get -2 or +2, depending on which card player 2 is holding. And so we need to use the beliefs at this information set to figure out how likely each of those outcomes is. The beliefs that we calculated for player 1 say that in this information set, there's a 3/4 chance that they're here and a 1/4 chance that they're here under the current profile. And so their expected utility is 3/4 times -2 plus 1/4 times 2. And so at this information set, playing call gives an expected utility of -1. So these expected utilities for each action are like deviation payoffs, saying, what would I get if I switched to this action at this information set? But we can also use those deviation payoffs to calculate the expected utility if the player uses their current strategy at that information set. And so at the jack information set, where the strategy says always fold, they'll get a utility of -1. At the information set where player 1 has a queen, their strategy says to randomize, but they get -1 either way, and so that's their expected utility. And at the information set where player 1 has a king, their strategy says to always call, which gets them a utility of 2. Now, as we proceed up the tree, we can look at each of the information sets on player 2's turn. And at the blue information set, playing fold always gives a utility of -1, whereas playing call can give player 2 either -2 or +2, depending on player 1's card. So again, we'll use the beliefs, which tell us that player 1 has a 2/3 chance of holding a king and a 1/3 chance of holding a jack. So player 2's expected utility is -2/3. At the purple information set, it's still the case that if player 2 folds, they'll get -1. But if they call, they'll get -2 every time, because they're holding a jack, so they will always lose. And so our expected utilities are -2 for call and -1 for fold. At the cyan information set, player 2 is holding a king, so when they call, they always get +2, whereas if they fold, they still get -1. For the remaining information sets, the calculation is a little more involved, because playing pass results in a terminal node, but playing bet results in a continuation of the game. So at the green information set, where player 2 is holding a queen, when they pass, they could get -1 or +1, depending on player 1's card. So we need to use the beliefs to figure out the probability of each state. And since there's a 1/3 chance that player 1 is holding a king, we will 1/3 of the time get -1, and 2/3 of the time get +1, for an expected utility of 1/3. At the orange node, player 2 is holding a jack, and so passing always gets them -1. And at the pink information set, player 2 is holding a king, so when they pass, they always get 1. But now we have to figure out, at the green information set, if player 2 plays bet, what will be their expected utility? Well, at the green information set, there's a 1/3 chance we're at this state and a 2/3 chance we're here. And if we're at this state and play bet, then we end up at the information set for player 1, KPB, where player 1's strategy says always call. And so when we play bet, we know that we'll end up at this outcome, where player 2 gets -2. But 2/3 of the time, we are at this state, where playing bet leads us to the information set for player 1, JPB, where player 1 is always playing fold, in which case we end up at this outcome, and player 2 gets +1. And so the expected utility of playing bet at the green information set is 0. At the orange information set, there's a 2/5, 3/5 belief distribution. And if player 2 chooses bet, then in the first case, we'll end up at the information set where player 1 always calls, meaning player 2 will get -2. And in the other case, we'll end up at the information set where player 1 mixes 50-50, and so half the time player 2 will get -2, and half the time they'll get 1. And so in the case where player 2 is holding a jack, betting gets them an expected utility of -11/10. Finally, in the pink information set, there's a 3/7, 4/7 belief distribution. And in the event we're here, playing bet puts us at the information set where player 1 mixes a half, and so player 2 will get 2 half the time and 1 half the time. And if we're at this state, then we end up at player 1's jack information set, where they always fold, and so player 2 gets +1. For a deviation payoff of 17/14. As we did for player 1, we can calculate the expected utility of playing the actual behavioral strategy by multiplying these deviation payoffs by the strategy probabilities. And then we can finish our walk up the tree by calculating deviation payoffs at each of player 1's top information sets. At this information set, we know that there's a 50/50 belief distribution. And if player 1 chooses to bet, then we end up at these information sets for player 2, where their strategy says to mix either a half or 0/1. And the possible utilities player 1 could get are 2, 1, 2, or 1. So playing bet gets player 1 an expected utility of 5/4. And we can do a similar calculation for the case where player 1 has a queen. At this information set, when player 1 plays bet, we arrive at player 2's cyan or purple information sets, where they respectively randomize either 1/0 or 0/1. And the possible outcome utilities for player 1 are respectively -2, 1, 2, 1. And so the expected utility of playing bet is -1/2. And then at this information set, when player 1 plays bet, we arrive at the cyan or blue information sets for player 2, where they play either 1/0 or a half. And the respective outcome utilities for player 1 are -2, 1, -2, 1. And so player 1's expected utility, if they bet here, is -5/4. Now, for the information set where player 1 has a king, if they are considering a pass action, we could arrive at one of two information sets for player 2. And if player 2 passes, we could end up at this outcome or this outcome. Or if player 1 plays bet, then we end up at this information set for player 1, and we've already computed player 1's expected utility when they arrive at that information set. And since player 2's strategy is to randomize 2/3, 1/3 at the green information set and 1/3, 2/3 at the orange information set, we know that there is a 1/2 times 1/3 probability of this outcome, and a 1/2 times 2/3 probability of this outcome. Since the total probability of these outcomes is a 1/6 plus a 1/3, the remaining probability of a 1/2 is on reaching the information set, where we know the expected utility is 2. And so, because the utility is 1 half the time and 2 the other half the time, the expected utility is 3/2. From this information set, playing pass will lead to the pink or orange information sets for player 2, where their mixed strategy is either 1/0 or 1/3, 2/3. And so this outcome never happens. This outcome happens a 1/2 times 2/3 of the time. And the remaining 2/3 probability corresponds to arriving at this information set. And at this information set, our expected utility is -1. And so the expected utility of passing is -1/3. Finally, from this information set, when player 1 plays pass, will end up at player 2's pink or green information sets, where they either play 1-0 or 2/3, 1/3. And so we never end up at this outcome. We end up at this outcome 1/6 of the time, and we end up at the information set 5/6 of the time. But since both the information set and this outcome give player 1 a payoff of -1, that's their expected utility. We can finish by calculating player 1's expected utilities if they play their mixed strategy. Here they'll get -1 1/4 1/3 of the time and -1 2/3 of the time, for an expected utility of -13/12. When they have a queen, they have equal probability of getting -1/2 and -1/3. So their expected utility is -5/12. And here their expected utility is 2/3 times 5/4 plus 1/3 times 3/2. So that gives an expected utility of 16/12, which reduces to 4/3. So we've now completed our full traversal down the tree to compute beliefs and back up the tree to compute expected utilities. Since I did all of this by hand, it's almost certain that I've messed up at least one of these. So you should double check my calculations and let me know where I went wrong. But given these expected utilities for each of the information sets and for each of the available actions, we can now easily compute deviation gains. For this first information set, player 1's expected utility if they play their current strategy is 4/3, and we can take a difference between their deviation payoff and that expected utility to get the gain. Since 5/4 is less than 4/3 and we floor gains at 0, the bet action has a gain of 0, but the pass action has a gain of 3/2 minus 4/3. And so the pass action would have a gain of 1/6. And so these gains of 0 and 1/6 would be added to the cumulative gains that we have for these actions at this information set up to now. But before we add those gains on, we have to multiply by the probability that this information set is reached, and the total probability of arriving at any of the nodes in this information set is 1/3. For nodes that are further down the game tree, we will multiply by the probability of reaching that information set if the player that the information set belongs to is deliberately trying to get there. And so that means when we're calculating the probability of this information set, we would multiply out the probability on each of the edges down the path to these nodes, but we would skip any probabilities that belong to player 1. So for this node, we would get a probability of 1/6, skip this, and then we would multiply by player 2's probability of B, which is 1/3. So we would get 1/18 plus the probability of this node, which is 1/6, then we skip, times the probability of B from here, which is 1/3. So again, 1/18. Adding those up, we get a probability of arriving at this information set of 1/9 when player 1 tries to get there. And so we would take the gains that we calculate for this information set, which in this case happen to be both 0, but if they were non-zero, we would multiply them by 1/9 before adding them to the cumulative gain for each of these actions. Doing this probability weighting accomplishes a couple of things. First, it helps us to perform larger updates at the more important parts of the game tree, because the probabilities we're multiplying by will be larger for the information sets that are more likely to be visited. And second, these probability weights ensure that the sum of the action gains across all of the information sets in the game tree will be closely related to the overall gain for the profile of behavioral strategies, which connects our counterfactual regret matching that's performing an update at every information set to normal form regret matching that's performing updates for each strategy. And making that connection helps with analyzing the algorithm's overall convergence. So, in summary, the counterfactual regret minimization algorithm is to, on each of t iterations, get a current mixed strategy by normalizing the gains at every information set. Then, using the current profile of strategies, we will traverse the tree down to get beliefs and back up to get expected utilities. Then, using those expected utilities, we will calculate gains for every action. Then we will weight those gains by the probability of the information set occurring. And finally, we will add the gains to a cumulative gain that we are tracking for every action and information set. And once we have updated all of those cumulative gains, we will do another normalization to get a new strategy profile for the next iteration. And because the probability weighting creates a close correspondence between counterfactual regret minimization and normal form regret matching, it's possible to prove that on any two-player zero-sum game tree, counterfactual regret minimization converges to a Nash equilibrium. In games that aren't zero-sum or that have more than two players, we don't have a guarantee of convergence to Nash. But we can still think of counterfactual regret minimization as an incomplete algorithm that might sometimes give us an equilibrium. And in addition, there are many extensions to CFR that can help it to use random sampling or apply to abstracted or incomplete game trees. And so this algorithm serves as the starting point for many large-scale systems that have tackled things like Texas Hold'em poker or other gigantic extensive form games.